Here we're going to look at question 9 from section 2 of the ENGAA specimen paper. So in this question we're told we have a telescope which is made up of three cylinders, each of length 20 centimetres, but they have different masses. So the smallest one has a mass of 0.4 kilograms, then the next one has 0.6 kilograms, and the final one has a mass of 1 kilogram. So we're told that this telescope is kept at equilibrium on a pivot point here, which is a distance which I've labelled as x bar from the end of the least heavy cylinder, or from the end of the least heavy cylinder. So with this information, the question asks us to find x bar, or the distance that the pivot is from the end of, or the lightest end of the telescope. So if you'd like to have a go at this question yourself, then just please pause the video now. Otherwise, let's have a go at it ourselves. Okay, so to go about finding x bar, we can try and think about the point at which our pivot is going to be. So, one of the things we actually know, or we can tell, is that this pivot is going to be at the centre of mass of our telescope. So that's because the centre of mass is literally defined as being the point at which there's no acceleration or no torque at all about the pivot. So it's the point at which the moments of our telescope, or the moments either side of the pivot, are balanced. So to find x bar, we simply need to find the centre of mass relative to this end of the telescope. So how do we go about finding the centre of mass? Well, there is an equation for it, and that equation is this: that the total mass of the object multiplied by the position of the centre of mass is equal to the masses and positions of each of the parts of the object multiplied together and all added together. So to find the position of the centre of mass, we simply need to find the total mass, which can be easy since we just have our three masses, and we need to find the position of each of the centre of mass masses of each of our cylinders. So again, this is going to be quite easy. What we can do is just simplify our diagram a little bit. So if we make it into just a simple straight line, then we have our the centre of mass of our 0.4 kilogram section, and since that's 20 centimetres long and symmetrical, we know the centre of mass is going to be right in the middle of that section. So it's just going to be 10 centimetres along from the end of that telescope. Considering our 0.6 kilogram section, then we know that since again it's symmetrical, it's going to be just 10 centimetres in the end of that section, so 30 centimetres in total. Doing the same thing for our 1 kilogram section, we know that the centre of mass of it is just going to be 50 centimetres from the end of our telescope. Okay, so now what I've done as well is just label that on here just to make it a bit more obvious what's going on. Now with these positions of the centre of masses, we can go ahead and find the centre of mass of our telescope as a whole. So we can just substitute these distances into our equation alongside the masses to get this. So our total mass is just going to be our 1 kilogram plus our 0.6 kilograms plus our 0.4 kilograms, and then these are going to be the masses multiplied by the positions of the centre of mass of each of the points, which is converted here into metres. So of course we can just go through and multiply each of these sections, add them together, to get the 2 multiplied by the position of our centre of mass is just equal to 0.04 plus 0.18 plus 0.5, which we can add together to get 0.72. Finally, dividing by 2 gives us the position of the centre of mass is just 0.36 metres, which corresponds to answer C given in the question.